share screen. I think someone said AA. Oh, y'all are talking about iClicker. I don't know what the... Anybody with a handheld iClicker, can y'all tell me what frequency y'all are on? Or enter it in the chat. Anybody? They're saying, what? Somebody said it's not AA. You have AA. Okay, so anybody else have AA? Raise your hand. That works for AA? Couple of hands up. Okay, so it's AA. Not yet. Not yet. I was waiting. It was weird. It was open. I want to talk about it in just a second. Okay, and I need to close this. Attendance. We're going to try this differently. Screen. Ha ha ha. Okie dokie. Now how do you get out of it? Okay. Okay. Let's do this real quick. So attendance is open if y'all want to go ahead and check in and tell me if you are present in the classroom or remote at home. Y'all can go ahead and do that. Okay, we'll go ahead and get started. So I wanted to tell y'all that y'all did really well on the exam. Y'all did really well on the exam. The class average was a 75. So y'all did very well. So I'm very proud of you. I know y'all worked very hard, and I appreciate that. If you have any questions, if you want help on something you got wrong because you know you're going to see it on the final exam again, please, please, please reach out to me and set up a Zoom appointment and I will help you. I'll do everything I can to make sure you succeed, but you got to reach out, okay? So remember, I have like open office hours, but you got to do it through Zoom. So at the beginning of the Moodle page, right, it has all my contact info and there's a link, it says appointments. That's how you make a Zoom appointment with me, okay? But I thought y'all did really, really well, so I'm very proud of y'all. Let's see, I think for some reason iClicker's opening spontaneously on me and I don't know what setting I have. So if you had an attendance from today already, I closed it, I'll clear it out when I get a minute this afternoon. I don't know what's going on with it, but I'll try to get it figured out. All right, trying to think if there's any other housekeeping stuff before we go on to chapter 3. Oh, I posted y'all like an extra lesson over the weekend, so that gets us caught up on the day that we missed. So we're not making up time in the classroom. I know that some professors are requiring y'all to come in like at night or over the weekend or something like that to make up the time that we missed during the hurricane. I think that's really, really difficult. And so I just posted y'all an extra lecture and said, okay, that covers it. If you have any problems with that, come and talk to me, but I think that's the most I can make it as easy to digest for everybody as possible, okay? I know we all have things going on. I just can't do it. So, any questions before I get started? I feel like I'm missing something, but maybe not. Okay, all right, so chapter 3. We're moving on from the nucleus, right, into the electron cloud, different part of the atom. So you should have watched sections 1, 2, 3, and 4, right? So then we have 5, 6, and 7 that you'll watch before class on Thursday. Everybody keeping up with the videos? I've noticed that on YouTube, I can see how many people have watched the video. I can actually go into Moodle and I can see which of you have clicked on the link to watch and which of you have not. So please, please make sure you are watching the videos before you come to class. This will make so much more sense if you're watching the videos beforehand. Otherwise, you'll be a little bit lost. Okay? All right, so let's try a few iClicker questions to see if you have paid attention when you were supposed to be watching some videos. Okay, I'm trying a new program out to make this hopefully a little easier to write on. So we're going to try this. All right. I'm going to stop that poll. It was 77. Start a new one. So how many protons and electrons are present in the sulfide ion S2-? How many protons and electrons? You can use any resource you have at your desk. This is participation. It's not a test. So a periodic table would be a really good thing to always come to class with. And if you go to Moodle, you can get the link to the periodic table that's in your book. If you want to like download that to your computer, that's fine. But you do need to come with a periodic table and a calculator. You will need a calculator at some point. Okay, I'll give y'all till a minute 30, because I know some people had to go find a periodic table. So a minute 30. Okay. All right, so what did we say? Well, we have a little bit of a range here. right? So what you should have said is E, so YE. So if you go to the periodic table and find S, what is S? Sulfur. So you find the atomic number. Where's the atomic number? Is it the top number or the bottom number? Top number, right? The whole number. So S should be 16, right? So you should have 16 protons. How many electrons should you have? 16, but that's a neutral atom. Is S2 minus neutral? No, it's not. So if it's 2 negative, that means you have 2 more electrons than protons. So what that does is it takes your proton number, add 2 more, and then you get your electron number. So be careful with that. So a negative means you have 2 more electrons than protons. Yeah? All right. Let's try another one. Okay. What ions are formed when magnesium transfers electrons to chlorine? And I'll give y'all just a minute on this one. Thought we had like 77 people. Come on, y'all. I'll give y'all another 1:15, 1 minute, 15 seconds. Come on, click in. Even if you have to take a guess, don't leave it blank. Okay, 1:15. All right, so what did you guess? Ooh, we're a little bit all over the place. Okay, so magnesium is in group 2A. How do you know how many valence electrons are in any given element? You look at the group. If you're group 1, how many valence electrons do you have? That first column. 1 valence electron. It's really easy. Group 2, and these are the A's, right? 1A, 2A. 2 valence electrons. Now you're going to skip over all of those transition metals because we're not really going to worry about those right now. And we're going to get to group 3A. What's another way to say 3A? You could say group 13, right? How many valence electrons? 3. Ooh, what did I do? Oh my goodness. Right. Is there an undo button? Let's see. I don't know. See, this is what happens when you try something new. What's that? There's an X at the top right. This one? Oh, here. Ooh. There we go. Oh, thank y'all so much. Okay. All right. So 3A is 3 valence electrons. So on and so on and so on, right? Until we get to 8 and we have 8 valence electrons. Really? This one's pretty easy, right? So magnesium is in group 2A, so 2 valence electrons. What's it going to do? It's either going to lose 2 or gain what? What are we trying to get to? An octet, 8. So are we going to lose 2 or are we going to gain 6? What's the easier thing to do? Lose 2. It's really easy to lose 2. It's really hard to gain 6. So you're not going to gain 6, you're going to lose 2. So if you lose 2 electrons, now you have 2 more protons and electrons and you become a +2. Okay? Y'all got to get this one. Chlorine 7A, so 7 valence electrons. So either it's going to lose 7 or gain 1. In this case, it's going to be easier to gain. So we're going to gain 1, so we're going to become a -1 charge. Okay? Let's try Try another one. Select the correct match. Oops, I didn't do it. Between name and formula unit. Name and formula unit. Sorry, I'm not showing the time. 1 minute. Well, this one actually might take you a minute. I'll give you 2 minutes on this one. And you can always use scratch paper when you're doing these. Oh, we almost got everybody. So you got about 10 seconds left. So, let's see, what should you have gotten? You should have gotten magnesium sulfide. What did the other popular one was A. You have to look at the charge, right? This is the crossover method that I've taught you in the video, right? Potassium chloride, it's a +1, chlorines, a -1. You cross them over, but they're both 1s. The only one that was correct was magnesium sulfide. But what did you have to remember to do? You need to reduce. So they're both a +2. So if you swap those from charges down to their subscripts, you have to reduce 2 and 2. They're both divisible by 2, so you reduce that to 1 and 1, but we don't write the 1. So be careful that you reduce. All right, let's go do some practice problems. And then at the end, if we have some more time, we'll come back to some quicker questions, okay? See if I can X out of this. I'm not used to using this. But we're gonna try it. Always good to try something new, right? You know, at least it's not Monday, it's already Tuesday. That's a good thing. So make sure you have a periodic table. You always, always, always need to have a periodic table handy. Oh, I gotta go by page. Okay. So, let's see how we can do this. We're gonna zoom. Nope. Okay, there we go. How many electrons are in each energy level of the following elements? So you need to have a periodic table next to you. So what column is H? What is H? Hydrogen. How many electrons? How many total electrons does hydrogen have? Total. Only 1. So you have to fill electrons in the lowest energy levels first until they complete that energy level, and then you go on to the next energy level. So we're going to put our first electron and our only electron in that first energy level. How about when we go to fluorine? How many electrons? Total. We look on there and it has an atomic number of 9. So what are we going to do? Let's fill that first principal energy level first. How many can go in there? Only 2. That's the one thing you've got to remember. That first principal energy level, you can only put 2 in there. So how many do we have left? 7. So we put those next 7 in the second principal energy level. Why didn't we have to go to the third principal energy level? Because we're not up to 8 yet. We didn't get to our octet. Okay, so how about argon? Argon has 18. So what are we going to do? We're going to put 2 in the first. How many in the second? 8. 2 plus 8, 9, 10. How many do we have left? 8. Oh, perfect. Okay, how about potassium? 19. So how many are going to go in the first energy level? 2. How many are going to go in the second? How many are going to go in the third? 8 or 9? We're going to put 8 in the third, and that last one is actually going to go in the fourth principal energy level. Whoa, what did I do? I don't know how to get rid of that. Okay, well, we're just going to ignore it. All right, now we're talking about valence electrons. Valence electrons are going to equal to the group, right? The group number in the A's and B's are going to equal to number of valence electrons. So carbon is in what group? Group 4A, so how many valence electrons? Aluminum, what group? 3 what? 3A. You could either put 14 and 13 here, or you could say the A's and B's. It doesn't matter to me how you do it. So how many valence electrons in aluminum? How about lithium? What group? Group 1A. How many valence electrons? I like this section, huh? This is pretty good. Fluorine's in what group? 7A. So how many valence electrons? 7. Nice and easy, right? If you know the group, you know how many valence electrons, at least for the main group elements. Okay, which of the following elements are stable as atoms? Tell me about this stable. How do we know something is stable? It has a full valence shell. That's a really important distinction. A lot of people just want to say it has an octet, but there are some exceptions to that, right? Where are my exceptions to that? Hydrogen and helium want how many? Want 2. Everyone else wants what? All others will say want 8 valence electrons. So a duet or an octet, either one is the goal. If you're in that first principal energy level, your goal is a duet for 2, but if you're in any of the other ones, you're looking for that octet. So beryllium, tell me about beryllium. Is this stable as an atom? No, it's not. So let's explain that. What group is beryllium in? 2A, so how many valence electrons? Is that, it's 2, it's a duet, is it good? No, because it's in what principal, in what period? What period goes across? Goes across is 2, right? So only the first period or the first principal energy level is okay with a duet. Everybody below that is not. So if you're in principal energy level 2 and below, 2, 3, 4, 5, 6, you know, I'm going down the periodic table. Those are wanting that complete octet. So this is not stable. How about argon? What group? 8A. How many valence electrons? 8 valence electrons. So this one is stable. Yes. Fluorine. 7A. So it has 7 valence electrons. Is it happy? Is it stable? No, not stable. How about xenon? Xe. What group? 8A. How many valence electrons? Oh, yes. 8 valence electrons. It's happy. It is stable. Okay. Go to the next page. All right, so section 2. Rocking and rolling. Maybe I should do this the full width so I can see the whole question. Nope, that was not right. Page width. Okay. What's the difference between a non-metal atom and its ion? Anybody want to help me out? I'm looking at the chat. What's the difference between a non-metal atom and its ion? It gains. Okay, so for our non-metal, our number of protons is equal to our number of electrons, non-metal atom, right? All atoms are by definition what? Oh, good morning. Wake up. All atoms are by definition charged or neutral? They're by definition neutral. So a non-metal atom is going to do what in order to become stable? It's going to gain or is it going to lose? It's going to gain electrons. So the anion will gain electrons to complete its octet. P-L-E-T-E. Right? So think, what's an example of a non-metal anion? Anyone? Fluorine. How many valence electrons are in fluorine? 7. So what are we going to do? We're going to gain that 1 to complete my octet so that I'm stable. Okay? How are the names of a transition metal atom and its cation different? So if we're just going to name the metal atom, what do we say? Just the element name. How about the cation? What do we call the cation? Remember an anion, we added IDE to it. But what do we do for a cation? If I want to say it's potassium, but it's a cation, what am I going to say? The potassium ion. So for the cation, we're going to say the element name. And then we're going to say ion, the word ion. So the potassium ion. So now we're going to start talking about.
We don't have to mention the Roman numerals for the transition now.
Well, that's a good point. That's a good point. We can add that. Oh, I did say transition. I didn't read that. Thank you. I didn't read that. I was just looking at that. Okay, so that's the cation. So this is for a metal, right? But this is a transition metal, right? Okay, so what are we going to do for a transition metal? How's it different? We're going to do the element name, right? Pick any transition metal, anything in this like in-between area. So gold. What are we going to say for gold? We're going to say gold 2, gold 4. But how are we going to say that? Let's say it's gold 4. We're going to put Roman numerals behind the name, and then we're going to say ion. So we have to add those Roman numerals for our metal, our transition metals. If it's in the main group, you just say the element name and ion. If it's a transition, you say the element name, the Roman numerals, and then ion. Okay? All right. Now we're going to start talking about charges when an ion's formed. Sodium, what's the abbreviation for sodium? Na. What group is sodium in? What group? 1A. Okay, so what are we going to put for a charge? This is 1A. Just a plus. Do we need to put the 1? No, it's just like writing formulas. If it's a 1, the 1's understood. Like in balancing a chemical equation, that 1 as a coefficient is understood. Same thing. All right, phosphorus. What's our letter abbreviation? P. So what group are we in? 5A. So what's our charge going to be? 3 minus. How did we get 3 minus? Right? So we said we want our octet. 8 is what we want. How many valence electrons do we have? We have 5. So 8 minus 5 gives us 3. So this is how many electrons we're going to gain. We're going to gain 3 electrons, and so it's going to give us a charge of -3 because we're always trying to get to that goal of that octet. So be careful that you know when you're transitioning from indicating the charge of a metal and indicating the charge of a non-metal. The metal's going to lose, the non-metal is going to gain. So be careful with that. All right, magnesium. My symbol is Mg. What group am I in? I'm in 2A. So I'm going to lose 2 electrons. My charge is going to be 2 plus. And it doesn't matter to me if you put the plus in front or the number in front. Doesn't matter. Okay, fluorine. What's my symbol? F. What group? I'm in 7A, so I have 7 valence electrons. I'm going to gain 1 valence electron for a charge of -1, but we just write the minus. Okay. All right. Oh, next page. All right, how many protons and electrons are present in the following ions? Okay, so I'm going to say protons, electrons. I'm going to kind of make a little table so I can kind of squeeze them in. All right, so aluminum, how many protons? I need 13. That's my atomic number. So what's going to happen to my number of electrons in order to get a +3 charge? I'm going to lose 3. So I need 3 less electrons than protons. So how many electrons? 10. Okay. Bromine. What's my atomic number? Atomic number is what? 35. So that's how many protons I have. How many electrons do I have? I have 1 more because I have a negative charge, so I'm 36. Hg, what is Hg? Anybody know? Mercury, and it is 80. So we have 80 protons, and if it has a charge of +1, that means that it has lost an electron. So I'm going to have 1 less, 79. Okay. Nitrogen, N3, what's my atomic number? 7. So that's how many protons I have. 3 minus means I have gained 3 electrons, and so I now have a total of 10 electrons. Okay. All right, now we're going to apply those naming rules. So Al3 plus, what are we going to call Al3 plus? Anybody? What is Al? Aluminum. Is this a transition metal? No. So do we need Roman numerals? No. So it's aluminum ion. That's it. Br minus. Now be careful. This is an anion, so we're going to name it a little bit differently. So this is bromine, and we're going to have to say it's an ion. So bromide. Remember, IDE is our ending for our anions. So that's bromide. Hg plus. Hg is mercury. M-E-C. I cannot spell. Mercury. Now, this is a transition metal. So you had to look on the periodic table and you had to correctly identify that this was a transition element. And so you have to indicate the charge in parentheses behind it, and then you have to add on the word ion. Okay, N3 minus. That's nitrogen, but we're not going to call it nitrogen because it's an anion, we're going to call it nitride. Okay. Let's see. Oh, yeah, and this one I did the wrong one, but that's okay. Name the following ions. Cu2 plus. Where'd you find that one on the periodic table? I heard it. It's a transition, so we got to be careful, right? So this is copper, what? The copper 2 ion. Ooh, look at this one, SO42 minus. Okay, so what we have to realize is this is not on the periodic table because it's more than one capital letter, right? You have more than one capital letter, that's telling you that I have two different elements present. So this is going to be a polyatomic ion. So these two are polyatomic ions. Okay, so go to your polyatomic ion table in your textbook, and then you have to go and search and find it. So do y'all have y'all polyatomics? Sulfate. And it is the sulfate, you could say the sulfate ion, or you could just say sulfate. Okay, HPO4 2 minus. Hydrogen. On an exam, I'm going to give you a polyatomic ion chart. You do not have to memorize that. Okay? So chart, polyatomic chart will be provided on the exam. Okay? In writing. All right. On to section 3. We are moving. All right, give the formula and name for the ionic compounds formed from the following pairs of elements. All right, we have potassium and chloride. So go and look on your periodic table. What is your charge for potassium? It's going to be a +1. How about chlorine? -1. We know potassium's in group 1. Chlorine is in group 7A, right? So if you have potassium +1 and you have Cl -1, you take those charges and you swap them. And that becomes your subscripts. So that turns into K1Cl1. But do we write the ones? Nope. They're understood. So it's just KCl. Final answer. Okay, zinc and oxide. What's my charge on zinc? Oh, does it say give the name? Oh, it is to give the name, the formula and name. Okay. How about a name? Potassium. Chloride. Right? We change the ending of our non-metal and we leave our metal alone. Unless it's a transition metal. Right? That's an exception. Okay. Zinc. What's my charge on zinc? How about oxygen? So what happens when we swap these charges for subscripts? They reduce to Zn1O1, and what do we end up with? ZnO. Why does that crossover trick work? What's the goal when we're writing an ionic formula? They want to balance each other out, right? We have to have an overall charge of 0. So if we have one atom that's a +2 and another atom that's a -2, what's my overall charge? 0, right? How about if you have a +1 and a -1? 0. They're not going to be all that simple, but so what is my name? Ooh, zinc. Zinc 2 Oxide. The charge on zinc is a transition metal, and the charge on zinc doesn't actually change. So I would accept either Zinc 2 Oxide or just Zinc Oxide. It is a transition metal, but it doesn't change. So I'll accept either. They got some strange ones, right? Okay, copper 1 and sulfide. Copper 1. What are we going to put? Cu. Copper. What's the charge? Sorry. It's okay. You're jumping ahead. What's the charge? +1. And sulfide. Do I go get that from a polyatomic ion table? How come? Because it ends in IDE. So I know that I'm going to get that off of the periodic table. So that is just the sulfur, charged sulfur atom. So what's my charge on sulfur? +2. So we're going to swap it and put this 2 as a subscript for the copper and the 1 as a subscript for the sulfur. And I'm getting so jammed up. Oh, thank you. It is. -2. So we should have Cu2, S. Do we write anything? No, it's a 1, so we're just not going to write it. I need to put some more space in these, huh? Yeah. I always underestimate how much space is needed to work out these problems. Okay. What's that? Okay, our name. What are we going to name it? We're going to name it copper, and we're going to say 1 because it's a transition, and a lot of times what you're going to see if you're given the ion name that you see that. So it's another red flag. Copper 1 sulfide. Copper 1 sulfide. Okay. 3.24, give the number of each type of ion present in each of the ionic compounds. Okay, so I just copied the ones again, but we said potassium chloride was what formula? It was KCl. So how many of each type of ion is present? So we have 1, what? K+ ion. You could say the word, you could say potassium ion, or you could write the symbol. Either one's fine with me, unless it asks you specifically for a name or a symbol, right? And then how about our other part of our formula, the chlorine? What do we have? 1 chloride ion. Now let me ask you something about a ionic compound. If I were to actually look at KCl or NaCl, am I only going to see 1 potassium and 1 chlorine atom? Is it going to look like, okay, let's say that this is potassium and here's chlorine. Does salt exist as these discrete 1 atom of this, 1 atom of that? Is that how an ionic solid works? No, what is it? All right, I see head shaking, that's a good thing. It's a repeating lattice. So for every 1 atom of potassium, we do have 1 atom of chlorine, right? So if this is potassium and this one is Cl-, right? It's a repeating pattern over and over and over and over again. If I can do this, right? I'm a little off, but it should. I can't switch it over, but it's a repeating pattern over and over and over and over again. So if you have salt in your salt shaker, right, you always have a 1-to-1 sodium to chlorine ions. It's always a 1-to-1 ratio. It's not that you only have 1. And that's going to be really, really different when we get to the covalent compounds. So make sure you understand the difference that you have molecules in covalent compounds, but in ionic substances, we have this repeating pattern. So really what this is, it's a ratio. It's not a molecule, it's a ratio. So you could have a tiny grain of salt that would have a 1-to-1 potassium to chlorine ratio, or you could feed your horse a salt block that's massive and you would still have a 1-to-1 ratio. Make sense? Okay, let's try another one. Zinc oxide, what was our formula? ZNO. What's my ratio? The ZNO was up here, it was a +2 and a -2, but then I just get ZNO. Tell me about my types and numbers of ions. What do I have? I have one Zn2+ for every one oxide ion. Because where do these numbers come from? How many of each ion I have? Where does that come from? It comes from the subscripts. It's not the charges, it's the subscripts. Okay. All right, so we have to give the formula and the name for ionic compounds formed from the combination of the indicated metal and carbonate, but in this one, we're gonna switch and we're gonna use the acetate ion instead of the carbonate. So let's do A. I skipped, I did skip C because I just ran out of room, thank you. All right, let's do C over here. Copper 1 and sulfide, thank y'all. Come back up to C, what did we have? We had 2, over here, we have 2 copper and we have 1 sulfide. So we have 2 Cu what? My charge. My charge up here is a 1. And then I have, how many sulfur? 1. 1 sulfide ion. 1, thank you. I'm saying one thing and writing something else. -2. Okay, so we had a charge, if you come up here, right? We had a charge of -2, so that tells us our charge. But when we look at our formula, we have a subscript of 1, so that tells us we have 1 sulfide ion that is a charge of -2. Okay. All right, 3.26 now. Now we're going to give a formula and name of the ionic compound. So tell me about sodium. What's my charge on sodium? +1. My acetate, I'm told this is a polyatomic ion, and it has a charge of what? -1. So I'm going to cross my charges and turn them into subscripts, and then remember to reduce if I need to. Okay, so what am I going to do? I get Na1, but I don't need to write the 1, C2H3O2, and it's a 1, but I don't have to write it. What if this number were greater than 1? If this number were greater than 1, if this were like a 2, I would have to make sure to put my polyatomic in parentheses. But we don't have to do that. Oh, I can't erase part of it. But we don't have to do that because we have a subscript of 1, right? But if you have anything greater than 1, you put polyatomics in those parentheses to make sure that we know that that's how many polyatomic ions we need, not just the element that's on the end, okay? All right, B. Fe2. So what charge is that? 2 plus, and we still have our C2H3O2. Now what am I going to do? Cross them over. Well, there's my negative. I didn't write that. Cross it over. That's a 1. So what do I write that as? Acetate ion, C2H3O2. Don't mess with the polyatomic ion formula. Don't mess with it, right? It has to say exactly the same or it's something different. And then we put our subscript. So it's telling us we have 2 of everything that's in the parentheses. So tell me, how many oxygen atoms do I have total in this molecule? 4. Okay. All right, and then we need to go back up and do C. Okay, C is aluminum. What's my charge on aluminum? My charge on aluminum is 3 plus, and my acetate C2H3O2 negative. I'm going to cross them over. So I get aluminum. It has a 1, so we don't write it. Now our subscript on our acetate is bigger than 1, so we have to put it in brackets, in parentheses. C2H3O2, and we put a 3. Now we have to go back and name these. Let's go name them, right? We have to name them too. Yeah. Okay, so what do we call A? Sodium acetate. I love polyatomics because you don't have to do anything to them. You just write their name. It's very, very nice. How about this one? How about B? Good job, y'all, for remembering those Roman numerals. Iron 2 acetate. And then our last one, aluminum. Do we need Roman numerals? Nope. Acetate. Good. Okay. Last one in section 3. Ooh, we're doing good. Give the number of each type of ion present in the ionic compounds in 2.6. Oh, man. Let's see. Can we... I don't think I can copy and paste in here. Huh. Okay, y'all have to help me out. All right. What was A? Let's see if I have it over here. Here, 6. So we had sodium acetate. So give the number of each type. How many sodium ions? We had 1 sodium ion. And then what else did we have? 1 acetate ion. That's it. How about B? B, we had iron 2 acetate. So even though we said iron 2, that's telling us the charge. It's not telling us how many. So we had 1 iron 2 ion, and you could write it, in this case I'm writing it as words, the other one I wrote it as symbols. Either one's fine. And then we had 2, right? We had 2 acetate ions. And the last one, we had aluminum acetate. So how many aluminum? 1 aluminum ion and 3 acetate. ATE ions. I could spell. So why did we need 3 acetate ions in C? We're trying to balance out the charge, right? So if we come down here and we look at our aluminum acetate, right? Our aluminum has a charge of 3 plus, but our acetate is only what? 1 minus. So if we only had 1 of each, what would our overall charge be? +2. Can an ionic compound have an overall charge? Absolutely not. So you need 3 acetate ions to get a -3 charge to balance out the +3 in the aluminum. So make sure and double check that when you're writing your formulas that you give an ionic compound an overall charge of 0. All right. Jake, what were you asking? What about on the exam? It's been a while. I'm sorry, I haven't checked the chat. Jake, if you put that in the chat. Okay. All right, let's see. What was next? Ooh, okay, in search of an octet. Now we are going to draw some Lewis structures. You can do it different ways. I like to have kind of a formula that I always go back to use. That's why I do that needed, available, shared method. If you learned it a different way and you are more comfortable doing it that way, it's perfectly fine with me, as long as you get to the end result, okay? So I'll show you some with the needed, available, shared. It works out super nicely, super nicely. So whenever we talk about needed, available, shared, let's do A first. H2O. How many do we need for hydrogen? What does hydrogen want? Only 2, only a duet. So we have 2 atoms of hydrogen, and each atom of hydrogen wants 2 electrons. How about oxygen? How many atoms do we have? Only 1, and how many electrons to make oxygen happy or stable? We need 8, for a total of what? For a total of 12. Okay, but do we have that many? No, right? So let's go to our periodic table and let's go find out hydrogen has how many? We still have 2 atoms of it, but it only has 1 electron. It only has 1 electron. Oxygen, we have 1 atom. How many electrons does each oxygen atom have? 6. So how many electrons do we have? And these are all electrons. Come on, y'all. How many do we have? 8. So if you look at the difference between needed and available, the only way that we can make all of the atoms have complete octets or duets, depending on what they want, is to share electrons. So the difference between needed and available is going to tell you how many bonds you're going to make. So what's my difference? 12 minus 8 is 4 electrons. But does a single electron make a bond? How many electrons make a bond? 2. So I need to divide it by 2 to tell me my number of bonds. So I should have 2 bonds. Y'all see where I got that? Okay, so we had available 8 electrons, right? How many did we use? If we do available minus shared, this will tell us how many we have left. We had 8 available. How many did we share? See, shared, how many? 4 electrons. So how many do we have left? 4 electrons. So when you draw your structure, you're going to give me a structure with 2 bonds and 4 electrons. So let's try to do that. If we have H2O, can hydrogen be a central atom? It can't, because it can only make 1 bond. So it can't be a central atom. It's never going to be a central atom. So that means my oxygen has to be a central atom. How many other atoms do I have? 2. I have 2 other ones. I have 2 hydrogens. So I'm going to put them on either side. And I know I'm going to need 2 bonds. So I'm going to connect my atoms. Now, how many electrons do I have left? I have 4, but when I put them on the molecule, they're in pairs. Either they're in bonded pairs or they're in lone pairs. So we've used up our bonded pairs. Now we have to put the rest as lone pairs. So we put them, can we put them on hydrogen? Why not? It's got a complete octet, so it's happy. So don't mess with hydrogen. Is oxygen happy? No, it only has how many? 4. Ooh, how many more does it need? 4. So we're going to put, that's supposed to be a dot. Okay, so we put them on the oxygen. Okay, good. And water is a really easy one to draw, and so you don't necessarily have needed the needed available shared method in order to do it, but it's a good habit to get into in order to solve more complex ones. So next one is C3H8. Okay, so we have B, not D, is C3H8. Okay, so let's do needed. Needed available shared. How many do we need? We have 3 carbon atoms. How many electrons in carbon? How many does it need? It needs 8. Then we have hydrogen. We have 8 hydrogen atoms. And how many does hydrogen need? 2. What do we get for a total? 40. Available. Carbon, we have 3 carbon atoms. Each carbon atom has how many valence electrons? 4. We have 8 hydrogen atoms. How many electrons in each hydrogen atom? 1 valence electron. So for a total of 20. Okay, so needed minus available will tell us how many we have to share. We have to share 20 electrons. It's a lot of electrons to share, right? Divided by 2 gives us how many bonds? 10 bonds. Okay, how many is left? Available minus shared tells us how many is left. So what do we have available? 20. How many do we share? 20. How many is left? None. That's going to tell me I have no lone pairs on my structure. It's a nice way to know what your structure is going to look like before you even draw it. Okay, so now, how do I draw the backbone of this structure? Can hydrogen be in the center? No. So let's start with our carbons. We know we're going to link our carbons together, and then we're going to have to attach hydrogens to those carbons, and we need to attach 8 hydrogens. So let's attach them and see what happens. Because carbon wants complete octets, right? So I do 3 on the ends, and then 2 on that one. Looks like every carbon has 4 bonds, every hydrogen has 1 bond. And did I use up all of my bonds? I have 3, 6, 9, 10. Not too bad, right? The more you practice this, the better you're going to be. The more you practice, the better you're going to be. Y'all know in your textbook, these questions come from your textbook, from the end of section questions. But if you go to the end of the chapter, there are additional questions. And all of the odd numbered questions, the answers are in the book. So like you turn the page, at the end of all the additional questions are the answers to the odd numbers. So you can go home and you can practice those. It just takes practice. All right, let's see. What was C? No, we have 2 more to go. So C is in 2. Okay. C is in 2. Needed available shared. What do we need? We have 2 atoms of nitrogen. How many electrons does nitrogen want? For a total of 16 electrons. Available. We still have 2 atoms of nitrogen, but each nitrogen atom only has how many electrons? 5. Okay, so that gives us a total of 10. So we have 6 electrons needed available shared that we're going to share. We divide by 2 to get our number of bonds. That gives us 3 bonds. Now, don't forget to do your available minus shared to give you what's left. So how many do we have available? 10. How many did we share? 6. How many's left? So we have 4 electrons left. So let's draw our structure. We only have nitrogen atoms, and we only have 2. How many bonds are going to be between the 2 nitrogens? 1 triple bond. Now, we have 4 electrons left. How can we arrange those electrons so that each nitrogen atom is happy and has an octet? Should I do this? Why not? 1 nitrogen has too many, 1 nitrogen has not enough. So that's not a good solution, right? What if we give each nitrogen 1 pair? Yes. Now both nitrogens are happy, they have a complete octet. Okay. Then we have, what's our last one? Scrolling up. SiF4. Needed, available, shared. How many do we need? We have 1 atom of silicon. How many valence electrons does silicon want? 8. Fluorine, we have 4 atoms of fluorine. How many does fluorine want? 8. So you could have done that as 5 times 8. It doesn't matter to me. For a total of? Available? We have 1 atom of silicon. How many valence electrons? 4. Okay, we have 4 atoms of fluorine. How many valence electrons in fluorine? 7 for a total of? 32. Okay. How many do we need to share? Subtract the 2. How many do we need to share? We need to share 8 electrons. But that doesn't tell us bonds, so we divide by 2, we get 4 bonds. Now I want to know how many I have left. So I'm going to take my available minus my shared and get my left. So I had 32 available. My shared, I only shared 8 of those 32. So how many do I have left? So I'm going to have to put a lot of lone electrons. But it's a good thing to kind of know before you start drawing your structure. Okay. How do I know what's going to be my central atom? Usually it's the first element that's listed. And we'll go into why it's that one. I don't think y'all have watched that yet. I know I recorded it, but I don't think y'all have watched that yet. It's the one that's the least electronegative, but I think electronegativity is our last section in this one. But you can basically look and say, okay, the first element is typically going to be my central element. Now I have 4 fluorine atoms, and I can only make 4 bonds. So what am I going to do? Put it all the way around and make 1 bond to each fluorine. Now I have 24 electrons. So am I going to put them on my silicon? No, he's got a complete octet. He's happy, but my fluorines are not. So let's start adding them, and we'll count by 2s. 2, 4, 6, 8, 10, 12, 14, scroll up, 16, 18, 20, 22, 24. We're good. Okay. All right. Okay. We got some more to draw. Now we're just loving this, right? if I have kind of a pattern, I kind of get in the zone. It's kind of a cathartic, I guess. All right. So draw the correct Lewis structure for each of the following covalent compounds. So we have CHCl3. What's going to be my central atom? Just looking at that formula. My first one is going to be my central atom, right? We know it's not going to be hydrogen. but typically it's that first atom. Okay, so let's do our needed, available, shared. Let's see if I can scroll down. Okay, so my needed, I have 1 carbon. How many does carbon want? 8. I have 1 hydrogen. How many does hydrogen want? 2. I have 3 chlorine. How many does chlorine want? 8. What is my total? 34 electrons. Now my available. Carbon has how many? I have 1 carbon. Carbon has how many? 4 valence electrons. I have 1 hydrogen. Hydrogen only has that 1 electron. And then chlorine, I have 3 chlorines. How many does chlorine have? 7. For a total of? Okay, so my shared is the difference between the two. So how many do I need to share? 8. But that's not bonds. I want to divide by 2, so I get 4 bonds. Now I need to do my available minus shared to get what's left. What's available? 26 were available, shared 8, so what's left? 18 electrons. Okay, so I'm going to have quite a few lone pairs to put on there. All right, so we said carbon's going to be my central atom. How many surrounding atoms do I have? Total, 4. I have 3 chlorines and 1 hydrogen. So I'm going to put them around my chlorine. Hydrogen, chlorine, chlorine, chlorine. Now, do I want to give hydrogen any lone pairs of electrons? Nope, it's complete. How about carbon? Nope, it's complete. So where am I going to put my lone pairs? All over the chlorine. So let's count by 2s. 2, 4, 6, 8, 10, 12, 14, 16, 18. And when you put those lone pairs, if you were going to be writing an exam for me, you would have to be drawing these. We'll do it a little differently because it's going to be an all-online exam. But be very careful. Think about your atom being inside of basically a box, and you're putting these lone pairs of electrons on the lines of the box. So it looks nice and neat. Otherwise, you're going to get confused, and if you are handwriting it in future classes, things like that, you're going to get it wrong. So be very careful about placement of those electrons. Does that make sense? I'm not looking at my chat. I need to keep looking at that. All right. Is that the? No. We have plenty more. All right. We're only on B. B is AsCl3. So B is AsCl3. Okay. So let's do our needed, available, shared. Y'all are going to be experts at this, right? Yes. Okay. So needed. What is As? Arsenic. How many does arsenic need? We only have 1 atom of it. Needs 8. Chlorine. We have 3 atoms. It needs 8 for a total of 32. Available. Arsenic. We only have 1 atom. It has how many? 5. How are y'all finding that out that it's got 5? What you looking at? Periodic table, we're looking at the group number to get our number of valence electrons. Okay, so we have 3 chlorines, and how many valence electrons? 7 for a total of 26. Okay, so our shared needed minus available, we get 6 electrons. Divide by 3, we get, divide by 2, you get 3 bonds. Thank y'all. All right, so available minus shared tells me left. Okay, so my available is 26. My shared is 6 electrons. How many do I have left? 20 electrons. All right. Okay. All right. So my central atom is going to be my first atom that's listed. And what's my first atom listed? Arsenic. So I'm going to put my 3 bonds. I could possibly erase. Okay, so how many atoms do I have? to put around my arsenic? 3, chlorine, chlorine, chlorine. Now I have to put my 20 electrons. Is my central atom happy? No, what am I going to do? We need to give it a lone pair, right? So let's count by 2s and then we'll fill in our surroundings. So that's 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20. Okay, let's see if I can go down. Let's see, we did B, we're on C. Cl2, chlorine gas. We could do the whole needed, available, shared, but I want to do a slightly different way because some of them are a little easier. So when you think about chlorine, if I told you to draw the Lewis dot diagram of just chlorine, what would you draw? It would only have one that's not paired. I'm not used to my pen being on a string. I gesture too much, right? So when we do our Lewis dot diagrams, right, we give each side one, and then we start pairing them up, right? So I'm going to pair them. So it's 7 valence electrons, and that's what the electron dot diagram does. So if I have another chlorine atom, I'm going to do the same thing. 2, 3, 4, and then I'm going to start pairing them. 1, 2, 3, right? For a total of 7. So what happens? Right in the center, those 2 electrons are going to be shared by both chlorine atoms to make a single bond. And you have a complete octet for both atoms. So do you have to go through the needed, available, shared all the time? No, but sometimes it's easy. Yes, ma'am. If it needed to share 2, then yes, you would make a double bond. So if you look on the periodic table, right, group 7A elements have 7 valence electrons. So if you are doing Cl2, it can only make a single bond. But if you're doing O2, is my next one O2? I don't think so, but let's show you real quick. What? It was in the last problem? See here, O2. So O2, if I just started with an electron dot diagram, how many valence electrons in oxygen? 6. 1, 2, 3, 4, 5, 6. Doesn't really matter, right? And here's my other oxygen atom. 1, 2, ooh, don't do that. 1, 2, 3, 4, 5, 6, right? So if I make this a single bond, is each oxygen happy? No, we don't have a complete octet yet. So this electron would come in, and this electron would come in, and you'd create another double bond, another bond, so you would have a double bond. So your end structure is what we have here. Right? Now, I think the next one, no? Do we have N2? I don't think we've done N2. Let's do N2 real quick. I just want to show you the difference. What if you had N2? Let's do this electron dot diagram style. Did we do N2? Okay, so if we do this not needed, available, shared, how many electrons? 5, right? What group are we in nitrogen? 5A, right? So if we make a single bond, does that satisfy the octet? How about if we make a double bond? Does that satisfy the octet? No. How about if we make a triple bond? Yes. So then our structure is a triple bond, and each nitrogen has a lone. Whoa. I went forward. I really went forward. Okay, here we are. All right, and each nitrogen has a lone pair. So it's all about how many valence electrons they have, how many they need to share, if it's going to be a single, a double, or a triple, right? And you'll get that same information if you do the needed available share. Either way is fine. Okay. I think we have one more. Do we have one more? D, C2H2. D, C2H2. Anytime you just have carbons and hydrogens, sometimes it's easier to do where you just draw the electron dot diagram instead of the needed available shared method. So let's do that. So carbon, how many valence electrons does carbon have? I have 2 of them. 4 each. 1, 2, 3, 4. 1, 2, 3, 4. Hydrogens, how many hydrogens do I have? 2. Spread them out evenly. My suggestion, spread them out evenly. So where should I kind of put them? What do you think? 1 on each side. And how many valence electrons do they have? Only 1. So I put my hydrogen, I put 1. So now I need to make bonds to complete octets. How am I going to do that? Let's connect our hydrogens first. So that's a single bond. This is a single bond. Now what do I need to do? I need a triple bond. So 1 bond is not enough. We don't have a complete octet. A double bond is not enough. We don't have a complete octet. But a triple bond, we do. So you just can't leave it like that. You just have to rewrite it a little neater. Okay. That's the end of that. But I have 120. Oh, we only have 3 minutes. All right. I'll call it. Questions? Anybody have questions? Come see me. I'll help you out. Practice, 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 practice. Oh, yeah. We'll pick up here. And I had a mistake. That's the one thing I wanted to mention. I had a mistake in the video. I named water, I named it dinitrogen monoxide instead of dihydrogen monoxide. So be careful about that.
So for the it says that I missed on the first.
Let's see if that's one of the days I just got wrong. Okay, does anybody on Zoom have any questions before I close out? And Jake, not Jake? Jake, what's your question about the exam? Oh, I did. Okay. Okay, all right. Yep. Okay. So no questions on the Zoom? All right, I'm going to go ahead and close that so that it can start to end. Okay. I am going to end. Maybe. Wait a minute. Here, end.